What I want to talk about today really is just to share the outputs of two of our low carbon network funded projects. We've got the LV templates project, and the final report was submitted to Ofgem on that on Monday of this week. And then there's the early learning project, which one of my colleagues ran, which finished a few months ago. But what I want to talk about really is not what we're planning to do. These are the actual outputs from the project, so you can maybe get an understanding of how at Western Power we're actually using what we're finding. Okay, we'll start with the LV templates project. We're currently monitoring 800 substations and over 3,600 remote feeder ends throughout South Wales. We're capturing 13 channels in each substation, 3 voltage, 3 current, 3 total harmonic distortion, real power delivered, real power received, and reactive power lagging and leading. The remote voltage monitors at the feeder ends are combined with the voltage monitor at the substation, so we can understand what's going on at the substation end, we understand what's going on at the feeder end, so we'll have a good idea of what's going on throughout the feeder. We're also working with npower. We've got 80 feed-in tariff meters that are being monitored, and we have, with the support of passive systems, a full 12 months data on 525 feed-in tariff meters from their system. So we have over 600 PV installations. These are domestic PV installations, so the whole project is on domestic PV, not high density solar farms. To start the project, we asked the University of Bath to look at how many PV installations we'd actually need for a credible outcome, and they did some statistical jiggery-pokery and came up with a figure of 250 PV installations for a 98% confidence, and we've got over 600, so we're quite pleased with the figures that we've got. We chose South Wales. The project bid to Ofgem was that it would be representative of at least 50% of GB networks, and we considered South Wales a good cross-sectional area with inner cities, suburbia, rural and ex-industrial areas. The main aim of LV templates was really to provide us with visibility of what's going on with the LV network, because it's always been a bit of a strange situation where the LV network is the part of the network that as a DNO we know the least about, even though it's the part of the network where most of our customers are connected to. So the idea was, to do a real study of the LV network and the associated feeder ends, and incorporate into that the low carbon technologies, particularly PV installations, so we can identify what stresses are actually occurring on the network and what voltage headroom we've got available to play around with. We promised to create a set of nationally applicable LV templates, which we've done. We've got 10 LV templates. There was 3 reports. One was the templates. The second one was to identify the impact of low carbon technologies on the network, which is what we call the stress report. And the third one was to share embedded generation data with National Grid to assist them with load forecasting. And the way that we were doing this was to see whether we could create a proxy feed-in tariff meter for one feed-in tariff meter in a local area that we could then predict what the other PV installations were doing, and we could scale that up as needed to give the National Grid a better idea of what generation was coming their way, and then to share the findings with all interested parties, including the other DNOs. And that will be done, well, starting today. That will be done throughout the summer. Okay, like I said before, there were 10 templates created by the University of Bath, and they had no, we gave them no steer on the number of templates we thought would be suitable, and we gave them no steer on any kind of electrical information. It was purely statistical. They gathered all the data and then they clustered it, and it clustered better into 10 distinct clusters. We then analysed those clusters to see which substations were in each template. This is just an example of template 2, which comprises predominantly of substations dominated by domestic customers. and the profiles on the left-hand box there are for all days, weekdays, Saturdays and Sundays, and the boxes to the right are the associated voltage profiles. So if you look at that one as an example, I'm not going to go through all 10, so don't worry. We've looked at various low carbon technologies and how they'd fit in with those templates, and in this one in particular, retail, workplace electric vehicle charging would be suitable, we think, maybe with a limited need to curtail it round about the tea time peak, or then the overnight electric vehicle charging would be suitable because demand is low, voltage is high. Heat pumps would be suitable, we believe, with insulation or heat storage with a limited time of day constraint, and PV would complement the grid in this particular case, because it would be generating at sort of peak times. CHP, AD, hydro and wind are difficult to comment on really, because the nature of the generation is not limited to the time of day, and we can't really predict what the weather's going to do. Right, the stress report. The stress report really specifically focuses on demand capacity and voltage headroom in the DNO networks, highlighting the effects of local low-carbon technologies and microgeneration on the existing network. Now, the key findings here, bearing in mind this is again this is purely domestic installations. The maximum aggregated generation from PV within a postcode was on average 81% of the declared capacity, which leading to a voltage impact on our network which was approximately 36% lower than what we thought it would be.
Was that average every year, or?
Yeah, and that was over a year. Yeah, last year, which wasn't a good year as far as sunshine goes. But this is peak output, mind. Okay, it's not kilowatt hours. It's the peak. So all we're concerned about is the highest point. And this was mainly in urban areas as well, because we do accept that there are areas, rural areas, where the voltage rise with small transformers and small conductors is a problem. This finding is key, as the current DNO network planning is based upon declared capacity of registered low carbon technologies. As such, there's a potential for DNO planners to more accurately assess the impact of low carbon technologies, avoiding unnecessary costly network reinforcement. I've put in a little bit about heat pumps, not that you're interested in heat pumps today, but there was a marked, noticeable difference with the substations that had heat pumps connected, and that's going to be subject of further investigation.
From a good news or bad news standpoint?
For heat pumps, probably bad news, because of the demand.
Can I ask a quick question?
Yep.
On your first point? Does that essentially mean that you theoretically could have 19% more?
Yeah, I'll get to that in a minute.
Sorry.
Everybody get excited.
Yeah.
First good news gigawatts.
Yeah.
Roll on.
Yeah. Right. I'll talk a little bit about statutory voltage limits, although it wasn't a part of the project. David touched on it. Over the 11-month period, when the report was produced, we've actually collected 96 million voltage measurements at 10-minute intervals from remote feeder ends. We've identified that for those monitored points, 99.6 of them were inside statutory limits, and any that weren't, we've dealt with and resolved. But as David mentioned, at the moment the statutory limits are +10, -6%. In Europe, it's +10, -10. This is basically because our network still essentially runs at 240, not 230. But the majority of our voltage profiles are at the higher end of the statutory limit, and this suggests that it may be viable to reduce the network voltage levels. It may also be worth considering lowering the UK statutory limits to +10, -10 to align with current EU standard. And if this is adopted, it could result in substantial benefits for both customers and network operators. To put a scale of value on the adoption of the EU limits, a 1.5% fall in energy use through a voltage reduction of 2.5% across only half of UK's ground-mounted distribution transformers, with an average of 150 customers per transformer, would save approximately 850,000 megawatts a year. And using Ofgem's fact sheet, average UK domestic electric customer of using 3,300 kilowatt hours a year at 12.8 pence a unit could save the domestic end customer over £100 million each year. And if the voltage reduction was more widespread, so if we did it at primary level, then you could save even more. Stress reports. I mean, this is just an example of voltage charts for, this is cluster 4, template 4, in high summer. And what we expected to see there, you can't really see it because they are so close. There's a black line and a red line. The black line is, there was 32 substations in this cluster which had significant PV installations on them. There was 150 substations that had none. And we expected to see during the daylight times the voltage levels rising due to the PV generation. And it hasn't happened. So there's no detrimental effect that we can see from a domestic PV on this particular project. Now, whether that's due to primary level tap changing, keeping it all down, but the predicted voltage rise, or what we thought we were going to see, we haven't actually seen. Right, the feed-in tariff report, the Proxy Meter, the idea, the ability to cost effectively obtain a real-time view of the output of multiple small-scale local PV installations via a single proxy feed-in tariff meter could aid in smart local network control, planning and generation forecasting. And this report examines the feasibility of such a proxy PV feed-in tariff meter. And the key findings is basically, yes, the use of a proxy metering can be adopted to accurately reflect the local distribution generation to the network, which could then be factored up. Now, this project did it at high-level postcode area. So in Wales, it's something like CF24, which is a postcode area within Cardiff. And we looked at PV meters within that postcode level, and we took each one and compared it to the others, and you could use one and use a scaling factor and scale it up. We're going to look into whether or not we can do it at a primary substation level, because I think that would give the visibility. One of the key output for this report is we could use this PV proxy meter across multiple postcodes, fed into the DNO SCADA system, linked to National Grid, so we'd have real-time PV generation information for National Grid. And this could provide National Grid greater visibility of the hidden demand, whilst improving their demand and spinning reserve forecasting capabilities. And that's something that we are working on with the National Grid. The SCADA link has been proved with test data, but there are some concerns over the security, data security, that need to be ironed out. Okay, the distributed generation capacity versus output. The installed capacity of PV installation does not represent the actual generation output seen on the LV network. The orientation and the bearing of each individual installation is critical to its output. And this, combined with solar irradiance levels in the project area, resulted in a maximum of 81% of the installed capacity being visible on the LV network. As network planning is based partly upon the maximum distributed generation, the effect of the above would be an overstatement of the installed peak rating, even though the annual kilowatt hour calculations of PV feed-in tariff was accurate. This finding, combined with the orientation of the panels, would mean that we could actually get even more than the 19% overstatement of peak rating in northerly parts of the UK, and slightly less in the south due to the variation in the solar radiation. So there is, it would appear at the moment, and it's going through our policy people at the moment, that there is headroom there on domestic PV installations that this project has highlighted. Okay, moving on to the early learning project, and this was a lot smaller project. This is a tier 1 project, and it collected data from a small housing estate in Crickhowell, South Wales, where all the houses they're all new houses and they've all been built with photovoltaic panels. And the key objective was to establish what effect high density of PV would have on the low voltage network. In particular, looking at the voltages for different sizes of LV mains. They ran 3 separate mains cables around the estate, 95 wavecon, a 185 wavecon and a 300, and we could switch between the 3 and see the effects. Monitoring was installed mid-feeder and at feeder end for each phase, and was complemented by extra data on PV output, tap change data and solar irradiance. Now, the key learning from this project is that the voltage is not significantly affected by the LV main impedance or by the panels, leading us to recommend revisiting the LV planning assumptions. When the PV units were installed, a maximum PV output of 37.8 kilowatts was calculated, with 10% of peak demand assumed. However, with the recorded data, it's clear that PV outputs did not reach this level. The maximum export actually only reached 29.8 kilowatts, which is 79%. So the LV templates, we were looking at 81% of the installed capacity, and this one has come out at 79%. So the two are in the same ballpark. So that suggests that maybe a PV efficiency or diversity factor could be implemented when we're looking at domestic PV installations. So finally, these trials really, just as a conclusion, have allowed us to explore what impact cable impedance has on voltage rise due to domestic PV. We've collected a large amount of high resolution data, which has allowed us to conclude that in this case, the impedance of the cables has negligible effect on the voltage. The other data collected has given us clearer understanding of how voltage at feeder ends relates to the LV main during different times of days and scenarios, including a property's net export of PV. Also, a view of how installed capacity can be affected by the orientation of a PV panel and its efficiency, meaning that a tangible effect on the distribution network is less than initially expected. And we're now currently assessing our planning policies with respect to domestic PV installations. And that's it.